Here we go with question one, quite a long one. So by all means, feel free to press pause and have a little think if there's anything you're not entirely sure of. And as ever, please do ask questions if you have them. I'll leave you to read the question yourselves. We're dealing with a pendulum which is oscillating, and we're given a graph of kinetic energy versus time. And the first thing we're asked to do is calculate in meters the length of the thread. Okay, to do this, we're going to have to go into our data booklet. Again, we're actually scrolling quite far down. You can see how fast I've gone there. To our simple harmonic motion topic. You can see there we've got the subject of the pendulum, and so we're going to use our equation, which is t equal to 2 pi times the square root of L divided by G. We're going to assume here that G is 9.81. Okay, now in order to do this, we know G. We need to identify t, and we're going to use our graph, which we're given, in order to do so. Now, common problem with this question is the correct identification of the period. And as you can see here I've identified the period as being 2.25 seconds. Now, this may seem quite confusing because if we look on the graph, you'll notice that our kinetic energy actually does two oscillations, if you like, in that time. So I thought we could address that. And then let me just quickly replace my data booklet with our pendulum here. I'm just going to get my pendulum going, and we should hopefully see what's happening here. Okay, I'm just going to get this quite nice and big. Here we go. We've got my pendulum, which is oscillating. You can see quite clearly the conversion of potential to kinetic energy and vice versa. Okay, now the question is, what's happening with that kinetic energy as it oscillates? So I'm just going to allow this thing to step through so that we are at our fastest position. That's the equilibrium position at the bottom here. And you can see there quite clearly we're at maximum kinetic energy, highest speed. And now we're going to put on a little period timer, okay, which will allow us to see what happens over one period. I'm now going to step through. So what we're, tell you what, I might take this off just now. We'll look at that one later. We're going to step through this. You know that one period of the oscillation should return my pendulum back to its original position. In other words, it should be at the next point we're in our equilibrium position, moving left. Well, if we step through, we have done quarter of an oscillation, and you can see we're at a point of zero kinetic energy. So at that maximum point, we're at zero kinetic energy. We then step back through. Okay, and we're back into the middle. So what we've done on our graph is we've gone from a position of high to low and back to full kinetic energy, and hopefully you can see what happens here is that as we step through, we go to a position of maximum again, and then finally, this is painfully slow, isn't it? Back through to our maximum kinetic energy position here. So the time, our time period here is the time for one oscillation, and in kinetic energy terms, it's the time for the energy to reduce to zero, back to maximum again, to zero, and back up to the top again. Okay, so that's one key point here. Okay, making sure we identify our period is 2.25. That's one marker. We then need to do the calculations, which I'm sure most people are okay with. And we need to be paying attention to the fact that we're stating our answer to an appropriate number of significant figures. Well, our t is given to 3 significant figures, sorry. Okay, g is also given to 3 significant figures, and so therefore we are allowed to give our answer to 3 significant figures. So there's a mark here for just thinking about the significant figures there. All right. We're then asked to label the point with the letter x, where the speed of the pendulum is half of its initial speed. Okay, and I've tried a little bit of working here to show you the way we think about it. If we're going from v to v over 2, we know that kinetic energy is proportional to v squared. Well, if the speed is halving, then what's happening to the kinetic energy is it is being reduced by a factor of 4. So we started at 20 millijoules. We're not looking for the halfway point here. We're actually looking for the points along this line here, for example here, which is our point X, where the energy has hit our quarter value. So any of these points would be valid here, obviously drawing a nice big X on there as well. Okay. We're then asked to consider the mass of the bob and show that its maximum speed is about 0.7 meters per second. Here we're just going to do a simple use of Ek equal to half mv squared. That's our kinetic energy equation. And we're going to just take a second to remember that the maximum speed comes when we have the maximum kinetic energy. So we're just going to come back and check our maximum kinetic energy. Maximum kinetic energy, 20 millijoules. And this is the bit which trips a few people up. We forget about the fact that we're dealing with millijoules. Well, 20 millijoules, we're going to stick into our equation. We've got our 20 times 10 to the 3. We've got also a mass, which is also expressed in 10 to the minus 3. So if you actually forget both of these, you probably end up getting a mark here. We'll do a bit of working through, and we'll end up with a V equal to 0.73. Now, in proving questions, it's always advisable to give an answer to more than one significant figure and then round. So you can see that the answer they're looking for is in one significant figure. Please show your answer to 2 or 3 significant figures first before moving on. Okay, before moving on. So do make sure that you're showing all of your working, not just some. Okay. 1D, this question now becomes a question about momentum. We've got a 75-gram bob, which moves then horizontally at 0.8 meters per second and collides with a small stationary object of the same mass. So we suddenly become into momentum question. It's always a good idea to have just a quick look and see if there's anything in our momentum and impulse section which might be helpful. Well, we've got the definition, we've got the equation here for momentum, might be useful. Okay, but here we should use the fact that we remember that in every collision, momentum is conserved, assuming there is no external force acting, and that's the case here. Okay, we've got conservation of momentum, therefore m1u1 plus m2u2 equals m1v1 plus m2v2, and we know also that the two masses are the same, so that allows me to do a lot of cancelling. Okay, all of these mass values are able to cancel. We also know that the two of them move off together, they stick together, and what that means is that v1 and v2 are equal to each other, and I've just called them v. We therefore have u1, which was 0.8, u2, well it's 0, is equal to 2 times the final velocity that they both move off at, and therefore 0.8 is equal to 2v. In other words, v is equal to 0.4 meters per second. Only one mark for this question. Okay, so we're expecting a fairly simple answer, fairly simple calculation here. Of more sort of difficulty is going to be your question about inelasticity. Now, this is where you need to remember the following, that an elastic collision is one where the total kinetic energy is conserved, and it's always a very good idea to write that down, both for the examiner and for yourself. We then calculate the initial and final kinetic energies. Okay, we know that at the beginning we've only got one kinetic energy because my U2 is equal to 0, so we can kind of ignore this part here. We end up with an answer of 0.024 joules. Similarly, in the final, we have to consider the kinetic energy of both of them, and we end up with half of the energy. I've just realized that I've written something completely stupid in my answer. Okay, final kinetic energy is less, not more, than the initial kinetic energy, and therefore the collision is inelastic. That's what we call in the trade a brain fart. My apologies. Okay, we're then asked to sort of revisit the sketching. Okay, we're asked to sketch on the axis a graph to show the variation now of gravitational potential energy with time for the bob and the object after the collision. To do this, it might be instructive to come back to this. Okay, now what you should be aware, if we just allow this thing to oscillate, you should be aware of the fact that as kinetic energy increases, potential energy decreases, and vice versa. And so therefore, anything that our kinetic energy is doing, our potential energy is doing the opposite. This is called inversion. Okay, so what we're expecting here is maximum potential energy when the kinetic energy is minimum. There's one mark for doing that. The other mark is comes from the fact, I'm just going to pause this because I'm getting distracted, comes from the fact that we had our collision. And what we showed in this question 1e was that half of the kinetic energy has been lost. Well, what that means is the maximum value of my gravitational potential energy can only be half of what the original value was, and this trace shows the original value. So from 1e, we know that half of the kinetic energy is lost, and so therefore we've got half of the amplitude. Okay, we don't need to explain where that energy's gone. However, we do need to show it in our graph. So there's 1 mark there for the inversion and 1 mark there for the halving of the amplitude. This is a long question. Okay. We then get involved a little bit of Doppler effect. Okay, the speed of the collision after the bob was measured using a sensor. The sensor emits a sound of frequency f, and this is reflected from the moving bob. Okay, so effectively what we've got here is our moving bob has become a source, effectively, or an emitter. I've put in inverted commas, so it's not really emitting, it's reflecting sound. And in this sense, the Doppler effect is going to occur. Now, so what you will get here in marking your answers, you will get a mark for simply mentioning that the Doppler effect occurs, and then a couple of marks for trying to explain it. Now, explaining the Doppler effect is a tricky one, and IB likes to see the following. It likes to see the fact that you've considered the fact that the wavelength of the reflected wave effectively reduces. However, we're still dealing with a sound wave, and it has a constant speed. Well, the combination of these two factors, decrease of wavelength but constant speed, means that my frequency, which is v divided by lambda, is going to increase. So really, you're getting a mark there for talking about the decrease in the wavelength, and a mark there for talking about the constant speed. Okay, so as ever, take some time to have a think about your answers, how they compared to mine, ask questions, and if you're satisfied, move on to the following tasks.